circuit evaluation. And it's important to make the distinction between problems and instances. So here the problem is a form of the question. Does a circuit output 1 on a certain input? And then an instance is a specification of this circuit and the input. And we need some size parameter of these instances. So then we say things like there are polynomial number of gates, or it runs in polynomial time. It's polynomial in this size parameter. And we can collect all of the problems of this form, or equivalent to problems of this form, into the class P, which is very informally the class of problems that are solvable in polynomial time with a classical computer. But then we can start to ask harder questions, like circuit satisfiability, where now the question is not what does the circuit output on a particular input, but is there an input such that the circuit outputs 1? And here an instance is specified just by the circuit. And we can, again, collect all of the problems that are equivalent to this one into the class NP for non-deterministic polynomial time. Informally, this is the class of problems that are checkable in polynomial time, given a proof of the answer. And here the proof is just these inputs that we feed into the circuit. And a lot of problems that we care about, natural problems, aren't obviously circuit problems, but there's a sense in which they're equivalent to ones. So you may have heard of 3-sat, where we have some formula that's the ends of ors. We could just write this as a circuit. And this is a restricted class of circuits. And yet there's some way that I'll say in a bit that this is equivalent to the general case. And the input to the circuit is just the satisfying assignment. Another example is traveling salesman. Does some graph have a Hamiltonian cycle? A way of visiting all the vertices exactly once. And if there is, an easy way of proving it is just providing that cycle or torque. But not all of these restrictions that we can put on the circuits, retain the hardness. So sometimes, we restrict the circuit enough, and there's an easy answer. And so, NP completeness or equivalence is based on the idea of reductions. So reduction from one problem to another is a mapping from instances of one problem to instances of another, such that if we can solve the second problem, we can turn that into an answer for the first one. And so, for example, in the case of 3-sat, to say that 3-sat is NP complete is to say that given an arbitrary circuit, I can produce some 3-sat formula that's satisfiable if and only if the original circuit is satisfiable. And so somehow restricting circuits to this restricted set is without loss of generality in a coarse sense. And this notion of completeness is not restricted to NP. For any class X, there's this notion that a problem is X hard if any problem in X can be reduced to it. So this means that the problem is at least as hard as any problem in X. And it's X complete if it's both X hard and in X. And this completeness gives us a sense of equivalence between problems up to polynomial overhead. And so, for example, it's not just NP completeness; we also have P completeness. So, for example, linear programming, any circuit evaluation problem can be converted to linear programming, and vice versa. And it's important to note, what completeness tells us. So, completeness is a worst-case property of families of instances. It does not allow us to say, given a particular instance, is this instance easy or hard? But what it does allow us to say is that, for some class of, say, NP-complete instances, if we had an algorithm that efficiently worked for all of those classes, for all of the instances in that class, then we could efficiently solve any problem in NP, which we don't think we can do. And so it means that there's at least some hard instances in that class, but we can't look at any particular one and say whether it's hard or not. So this P and NP are sort of the two of the most important classical complexity classes, and implicitly when I define them, I didn't allow there to be errors at any point, and all of the information and computation was classical. One way of loosening this up a bit is to allow the the verifier or the answer to have some error probability. This third is arbitrary, but as long as it's bounded away from a half, it's the same. And here, again, all of the information and computation is still classical. We get the classes BPP and MA. And then we get to the reason we're all here, quantum information and quantum computation. And here, BQP, or bounded error quantum polynomial time, is the class of things that are efficiently solvable by a quantum computer. And QMA, or quantum Merlin and Arthur, where Merlin is some all-powerful wizard that provides the proof, and Arthur is a efficient quantum machine that checks the proof. These are the quantum analogs of P and MP, or BPP and MA. And as we go down this slide, these classes get larger, right? Zero error is less than 1/3, and classical information and classical computation are subsets of quantum information and quantum computation, respectively. But we expect that at least some of these inclusions are strict. So in particular, we hope or expect that, for example, BPP is not equal to BQP. That there are things that we can efficiently do with quantum computers that we can't efficiently do with classical computers. And it's one thing to know that all of these complexity classes are for decision problems, problems with yes or no answers. There are variants for function problems where we want to get some number out that's not necessarily 0, 1, or for example, sampling problems. And we can have a similar landscape of complexity classes depending on which parts are classical and which parts are quantum. And so in the classical world, we had 3 sets as this canonical NP-complete problem. In the quantum world, the canonical QMA complete problem is called local Hamiltonian. So the input is a k-local Hamiltonian that is a Hamiltonian that is a sum of terms, each of which acts on at most k qubits. And note that here, local is not necessarily geometrically local, but only in the sense that there's a limit on the number of particles that each interaction acts on. And you should think of k as like 2 or 3 or some other small constant. But then in addition to the Hamiltonian, to get some formal computational problem, we need to specify these 2 thresholds that are inverse polynomially separated. And then the question becomes, is the ground state energy of this Hamiltonian less than A or at least B? And we're promised that at least one of these 2 is the case. And so problems of this form are almost trivially in QMA, where the proof is just the ground state, right? If the ground state energy of the Hamiltonian is less than A, someone can just give us the ground states and we can check the energy, but only to inverse polynomial precision, which is why this restriction on the threshold was important for it to be efficiently checkable, even by a quantum computer. And so, this restriction to local Hamiltonians is already, in some sense, physically motivated. Physical interactions are, local in this sense, but they're also often local in a geometric sense, in some small number of dimensions. And they also have other properties that come up frequently, like translationally invariant for materials and crystals and things like that. There's often, so in the generic problem, these terms can be anything, but in physical problems, they're often very particular types of terms. And maybe the coefficients vary across the system, but they're all of the same type. And even maybe of the same sign. And there's been a large and growing body of work showing that even these restricted classes of Hamiltonians are still QMA complete. And the power of results like this is that it allows us to say something about the hardness in an algorithmic independent way. So without these tools of complexity theory, we can look at an instance or a set of instances in a particular algorithm and analyze the performance of this algorithm on this set of instances. But by showing that a restricted class of problems is QMA complete, it gives a lot of evidence, maybe not a formal proof yet, that there exists no algorithm that can efficiently solve all of the instances in this class. So this generic local Hamiltonian problem is defined on qubits or qubits. Often in physics and chemistry, we want to answer questions about systems of distinguishable particles, either bosons or fermions, as you wish, and even more restricted classes like the Hubbard model, where we have some lattice and there are only two types of terms. And some variants of this problem are also known to be QMA hard. We fix the particle number, and maybe there's different parameter regimes. Maybe it's known for all of them. And so these results are very nice. They get us closer to showing hardness of problems that we care about. But sometimes there's still something artificial about the types of systems that we can prove hardness for. So for example, in these Fermi and Bose-Hubbard results, we have arbitrary graphs, which is not what we have in physical systems. And so there's been a lot of progress in proving hardness for physically motivated systems or physically realistic systems, but it's not complete. We're still trying to push this and see what we can say about the exact problems that we care about in practice. In quantum chemistry, the sort of fundamental problem is electronic structure. So within the clamped nuclei approximation, we fix the nuclei in space, and then basic electromagnetism gives us the Hamiltonian of the system. And so we can ask, how hard is this problem that so much of quantum chemistry is based on solving? And to answer that, first we need to formalize it as a formal computational problem. The true states of these systems exist in the continuum. We need to first specify the single particle orbital basis that we're solving the problem in. We specify some external potential. Maybe it's from the nuclei, maybe it's some more phenomenological model. And then for technical reasons, we also need to specify these thresholds. And we can ask the question now, is the ground state energy of a Hamiltonian like this less than A or at least B? And James, our collaborators, and I have shown that even this very, very structured problem is still QMA complete. Again, there's some limitations in our results. The orbitals that we use are quite artificial in some sense, but it answers a lot of questions like what structure can we keep or impose on the system and still retain hardness. So that's all about hardness, showing what we can't do with either classical or quantum computers. But we also want to actually compute things when we can. And so the main idea of quantum algorithms for physical problems is to represent the quantum state that we're simulating on the quantum computer. And one challenge in doing this is that if the simulated Hamiltonian is fermionic, we need some way of mapping fermions to qubits and vice versa. And this is an area that James has done a lot of work, a lot of great work that he'll tell you more about. And once we do that, we need to map not only the states but the operators as well. Maybe we want to do time evolution. Maybe we want to prepare some variationally specified ansatz state. And so when we talk about BQP and QMA, it's often the question of polynomials versus exponentials. But in practice, degrees of polynomials and constants really matter, right? There's a big difference between n squared and n cubed, or even between like n squared and 1,000 n squared. And so there's a lot of work that goes into optimizing both the algorithms and the compilations of the algorithms. And this is one place where better or variety of fermionic mappings can be very useful. And there's also trade-offs we can make between resources. So, I've primarily been talking about the time it takes to do things, but often, we can do things in less time with a few more qubits. And, theoretically, we can sketch out this landscape of trade-offs that we can make. But then which trade-off we actually make in practice will be largely dependent on the properties of the device that we're using. Like, are there a lot of qubits, or maybe there are fewer qubits that are very good? And so, we can design and choose our algorithms to get the best performance out of actual devices that we have. So this is all the technical tools that go into answering this very high-level question of what questions about physical systems can we compute efficiently? And algorithms give us one way of saying what we can compute, both in theory and practice. It's nice to say things. It's nice to say that there exist algorithms in theory, but there's also a bunch of additional work to actually implementing those in the most efficient way. And then hardness results, very informally say, well, we can't compute. And so these two tools together sort of narrow down what we can hope to do with quantum computers, and help to identify, for example, practically important chemistry or physics problems that we can solve efficiently with quantum computers, but can't with classical. So with that, I will introduce James. So I've known James since I was an undergrad and he was a grad student at Alana Spiro-Grzyk's group at Harvard, where he got his PhD in chemical physics. He did postdocs at NEC, Columbia, and Vienna, is now a professor of physics and chemistry at Dartmouth College. He's done a lot of excellent and unique work at the intersection of computer science and chemistry and physics. He's established the computational complexity of a lot of important and practically interesting chemistry problems, and has been really, I think, at the forefront of these qubit fermion mappings that are a very fundamental building block in solving chemistry fermionic problems on quantum computers. In addition to his excellent research, he's also an enthusiastic educator. So this should be an engaging and informative talk.
Yes, so thank you so much for the invitation and for the wonderful introduction. It's great to get an actual talk for an introduction. It's never happened to me before. So let me say I'm quite excited to give this lecture. Yes, 1 second to share my screen here. Okay. Moment. Too many windows open. Okay. Well, just wing the rest. Okay. One second, please. It's a shame considering how much I use Zoom, right? Here we go. Okay. So, okay. You guys can see my screen. You can hear me?
Yeah, it looks good.
All right, excellent. Yeah, so today what I want to give an introduction to is electronic structure on quantum computers. And I'll pick up where Brian left off. So Brian gave a very nice computer science introduction. I had a chance to talk to some of the people who are going to be listening beforehand, some of the people from the panel afterwards. And I got a sense of kind of what might be interesting to talk about here, given that this is such a large audience. So I figured I'd focus on things that are close to my heart, but I'd also try and bring in people who are perhaps further away. Brian did a very nice job of trying to bring in computer scientists, and I'll do my best to try and bring in physicists, and hopefully we'll all meet in the middle and understand what electronic structure and quantum computers might mean for quantum chemistry. Okay, so as an overview, I just wanted to say a few things about just quantum technology. Quantum technology right now is at its height, so much money, a lot of excitement, a lot of companies and being invested, from Google to IBM to Amazon to startups like Qbraid and Zapata, to Cold Quanta building hardware, Honeywell building hardware, AT&T thinking about communication, just a wide range of investors and interested parties in the entire quantum industry. This is extremely exciting. So as Brian mentioned, we met when he started grad school, but I started grad school a very long time ago, and there was no such thing as a quantum industry. There was no one actually thinking about building these devices. So now to actually see them coming to fruition, to see people actually starting to construct these devices, it's really, really amazing. So when I was in grad school, I was going to summer schools. Now most of my students are going to do internships. It also turns out to be a worldwide effort with efforts all around the world. As Brian mentioned, I was at the Vienna Center for Quantum Science and Technology. And there I got exposure to some ideas that I'll talk about a bit later, but you can see this is spread throughout the entire world, from China to Russia to Australia, India, and of course, the United States. This worldwide effort means that there's a lot of excitement inside of quantum computing, a lot of ideas and a lot of things floating around. So I'm going to try and bring in a lot of these ideas. I might take a more high-level approach here, but hopefully it will still make a lot of sense to everyone and keep everyone on the same page. So also feel free to ask questions. I enjoy questions. I enjoy stopping. I enjoy entertaining questions of that sort. So Brian mentioned we just finished a paper, and in that paper, one of the ways we had some discussion about how to start off the paper. And one of the things you'll find is this quote from Dirac. This quote from Dirac is quite a fantastic quote because it's in 1929, but it really sets the stage for almost the next 100 years, right? So the Schrödinger equation, which is governed by this Hamiltonian that you see in the middle, allows us to uncover the underlying physical laws necessary for the mathematical theory of a large part of physics, and the whole of chemistry are thus completely known, and the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. Now, I put in here the whole of chemistry, right? My talk will be focused on the whole of chemistry. Maybe not the whole of chemistry, but certainly the parts that intersect with chemical physics. We're talking about what we can understand from a molecule. Now, the other thing I like to have to introduce these talks, depending on where my audience is to kind of introduce it as a conversation piece. So Dirac says this quote about using, about trying to understand the physical laws through the equations that we have. But on the other side, we want to build quantum devices. If we can build quantum devices, that means that we understand the Schrödinger equation well enough to control a quantum device, that we have a physical qubit, some sort of implementation of a two-level system. We have some way of manipulating these two-level systems, coupling them two-level systems, and we have some way of measuring outputs, as well as initializing states. So the idea is that as we get better building quantum computers, we will also be able to understand the physics better. We understand the physics better, we can build better quantum computers. So it's a nice conversation piece where it goes inside of a circle. I like to also give here the analogy of building a new desktop or a new laptop or phone. You wouldn't do this without using a computer, right? So in the same sense that you use computers to design better computers, quantum computing also has that same sort of snake eating its tail to it. So as I mentioned, one of the things that I did want to try and bring in is everybody, right? So one of the things that I wanted to kind of do is set up this discussion. I'm teaching introductory quantum physics, and this is quantum physics without any formalism, just the physics. And where we're at now is just going through the gross structure of the atom. So atomic structure has this gross structure where you're using some reduced mass. There should be no E here, but some reduced mass of the electron, whatever the nucleus is, depending on how heavy the nuclei is, you can actually see this effect quite easily, I think, spectroscopically, depending on how much heavier the nuclei is than hydrogen. This also, you have to include relativity to get the fine structure. You get hyperfine structure from electron nuclear interactions. And these are all things that AMO physicists could tell you a large amount of things about. There's, of course, more corrections. You can go to subatomic structure and with higher energy scales. On the other hand, if we go to lower energy scales, then we get to chemical physics. We're looking at, instead of atomic physics, we're looking at multi-centered systems. And here we don't even take into account relativity quite often. Relativity enters in sometimes, but the Hamiltonians that we'll be focused on don't include relativity at all. The fine structure is something that we won't see. Hyperfine structure very rarely shows up inside of quantum chemistry. And I'll give some sense of why. But I'd like to first unpack this Hamiltonian that we have here. So we have the kinetic energy, again, p squared over 2m. We have our electron-nuclear interaction, and we have our electron-electron interaction. So all these interactions are what makes things interesting. This electron-electron interaction in particular makes things extremely interesting. If we have non-interacting electrons, do we actually have problems that we can solve classically? This is known as match gates. For those of you who might want some buzzwords inside of your talks, match gates is what you can go Google right now. But what the chemical physics this Hamiltonian gives rise to, rather than thinking of atomic physics, we started off with this gross structure, and we refine it to get fine structure and hyperfine structure. Here, we're going to take this chemical Hamiltonian, compute the electronic structure. With that electronic structure, we're going to then be able to understand vibrational structure, rotational structure, rotovibrational structure, protein structure. All of these things will be determined by the potential energy surface, which we get by solving this Hamiltonian for every different settings of the nuclear coordinates. So these RIA is the distance from nucleus A to electron I. And the charge of the nucleus being ZA times the electron charge, which we're assuming here is positive. The magnitude of electron charge, should I say. So all these things come together, and this is exactly how we want to think about what we're going to do. We're going to do the bottom half of this. We're going to think about chemical physics. We're going to think about what do we do in order to understand chemical physics, what sort of problems we need to solve. Okay. The better we can solve these chemical physics problems at the level of electronic structure, the better we can understand rotational, vibrational, and just the motion of nuclei at any higher energy scale. So as an example, here on the left, you'll see at the top is potential energy surface. And here on the bottom, it's a bit small. Maybe I can zoom in. Yeah, I can. Great. And this is a reaction curve from a review of modern physics by Bartlett. It's quite nice, explaining couple cluster theory, which I won't get into today, but that's also quite relevant for quantum computing. There's a lot of works being done on a couple cluster on quantum devices. But what I want to draw your attention to here inside of this figure is that there's a number of different lines, dark lines that you can see. This one, for instance, which would be the lowest energy electronic state. This would be the first excited state. Then above it is the second excited state. There's a crossing here. This is also a very interesting point inside of quantum physics because you get a lot of very interesting things happen, whether that crossing is you get conical intersections, you get a lot of things that can happen much faster due to this. What you see here, vertical excitations. This is a particular approximation that you go straight up. As you go up in this energy well, you end up with some, if you have the photon energy, then you go to the excited state. From that excited state, you might dissociate differently than if you cross the barrier height and go here to some reactions, products, some reaction that's occurred, then now you have BC instead of ABC. There's some barrier heights. These barrier heights are going to give rise to exponential dependence on the accuracy here. This is what's going to give us rate dependent rate. This is going to give us rates, which will be exponentially sensitive to our errors inside the potential energy surface that we have here. The potential energy surface also will define nuclear motion. And just like you would know from your harmonic oscillators, these are harmonic oscillator states, and these are just the vibrational states of the nuclei. So when you think of the nuclei vibrating, that's completely determined by the electronic structure. Okay, so this is why electronic structure is important for quantum chemists. But Brian mentioned this idea of the Hubbard model. In the Hubbard model and the TJ model and a lot of these other model Hamiltonians, you're not necessarily interested in small changes at Hamiltonian. You're interested in phase transitions and macroscopic properties that might arise depending on what the interactions are. In this case, we're really interested in very small changes, right? So some examples here are some instances of quantum computational chemistry instances. So every figure here is one electronic structure calculation. So you'd fix these nuclei inside of space, and you compute what the energy is here. Then you rotate one of the bonds. So you're rotating this to see one is in the plane of the page, one is out of the plane of page, one is into the plane of page, out of the screen, yes, out of the screen from you. And so you compute both electronic structures, and you calculate what's the difference. What's the barrier height? Barrier height being how much energy does it take to go from this side to this side. So this is the barrier here. And there'll be some barrier here, and you can rotate this, and you can see some nice oscillation inside the energies. Proton affinity, how much energy does it cost to add a proton to some system? Reaction energies, how much energy do you get by running this reaction? Radical stabilization energy, the same idea. We just compute all four of these different structures and actually take the difference. So this is the idea of what computational chemistry is all about. Okay, there's some message here. Yes, thank you. Crystal structures, magnetism, these are also interesting things that show up from the electronic potential energy surface. So again, if you think of crystal structure, if you're coming from more of a solid state background, you can think the normal modes will be determined by how tightly confined these, what the spring constant is between the nuclei. That spring constant is again determined by the curvature of the electronic configuration at equilibrium. Okay. Here, I'd like to give a plug to the Bohr correspondence principle. So this is very interesting to think about when we do and don't need quantum computers. So if we're thinking about high energy interactions, we're talking quantum electrodynamics, relativistic quantum mechanics, or just even atomic physics, where we have to bring in relativity just to talk about fine structure. Well, all these things require quantum mechanics. Molecules also need quantum mechanics. If you open up your chemistry textbook, it's actually quite amazing how quickly they go through all of quantum mechanics. They go through 4 different quantum numbers, no explanation. All electrons need a different set of quantum numbers, and you're done with quantum mechanics in 2-3 lectures. It's actually pretty amazing how streamlined that has become. In any case, from there, you can go on to talk about solids and liquids. This, again, you quite often have very good classical descriptions. So the free electron gas is a very nice description of metals, right? It actually works very well. You start introducing interactions later, right? Interactions show up in a very weak sense, but the Druid model actually does very well as a model for free electron gases. Okay, protein cells and viruses. If you're going to do a simulation of protein cells and viruses, you might calculate the potential energy surface, but then you would just do the entire propagation classically. To give you some sense of the different levels of quantum mechanics that we would be interested in. Yes. Okay. Next. Okay. So that's my introduction, orientation to what we're talking about, what the goals are for the talk. And then now what I want to do is talk a little bit about electronic structure on quantum computers. This will give us a chance to talk about some of the ideas that people have about using quantum computers. And that will then lead us into the third part of the talk, which is about competition for electronic structure. So how do we actually do, what is the competition for electronic structure on quantum computers? This will also give us a chance to revisit some of the ideas that Brian put before us about computational complexity, to think about what the limitations of the classical and quantum approaches are. Okay, so let me start first with this idea of universal quantum computer. A universal quantum computer, I'll take a very high level, bit dodgy approach here, is that we have some device, some algorithm that we're going to run. And this algorithm, before we run it, we need to initialize the computer. Some sort of way of initializing the system. Initialization and measuring are effectively the same thing. If I can measure it, I know what the outcome is. I can flip this bit and get back to the all zero state, and then I'm initialized again for the next run. Quantum algorithms start by doing some sort of set of gates, some sort of transformations, and these transformations should be done in polynomial time if we're considering something that's considered easy for a computer, for a quantum computer. And then at the final time, as Brian mentioned, you should be able to do the measurement with high probability and get out an outcome. So that's why it's bounded error. The error needs to be bounded away from 1/2, so I can actually read out something interesting. Otherwise, I'd have to sample all day to get out, decide if it's, 0.4999998, or if it's 0.50001. And this might take a lot of sampling if it becomes very close to 1/2, and actually get a very large amount of computational power if you actually put the boundary at 1/2. Okay. One of the things that I found, again, as I mentioned, this is something that I've been thinking about for 10 years now. In fact, this is from 2011. This is when this paper was published. Simulation electronic structure Hamiltonians using quantum computers. This was one of the first projects I finished in my PhD. And here you can see this is the table of all the parts that we'll talk about. Just to give you some sense, again, we have some Hamiltonian. This Hamiltonian was decomposed into a set of local terms, as Brian mentioned, 3, 4, or 5 local, ideally, maybe 2 electron interactions, 1 electron Hamiltonian. And then we're going to do a Trotter decomposition. This is just a way of approximating the unitary evolution. We do some sort of transformation to get these fermionic Hamiltonians into qubit Hamiltonians. And then we do an algorithm called the phase estimation algorithm, which allows us to read out a phase. We're going to read out lambda, and then you see this E0 here. One very, 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 very big asterisk here is that this size 0 may be hard to create. That's actually a huge caveat to all of the methods that people talk about quantum computing, is that it may or may not be possible to construct the initial state. And this is, in fact, what QMA is all about, the quantum Berlin author. So I said then and now. So this was then. This is the figure that we had 10 years ago. Now there's many things that have been improved, right? So first, this time evolution methods have been generalized in a whole host of different fashions. I've not been working on it so much, but there's been a lot of really fantastic work from Taylor expansions rather than Trotter approximations. You can have a way of doing a Taylor expansion, which is quite different than what you would do classically. If you do a classical Taylor expansion, you throw away terms, well, you don't have a unitary transform anymore. Here in the quantum setting, you do a Taylor expansion, but you have a way of projecting back to something that's unitary, or whatever the closest unitary is. The quantum singular value transform generalizes a lot of things that have been done into the last 4 or 5 years, from qubitization, quantum signal processing, and block encodings. So all these ideas are really being developed quite nicely. And I feel like the people who have developed it have done such good work that I don't want to step on their toes. People like Nathan Weeb and Andreas Gillian and Guanghao Lo, many other authors that have worked on this. There's, instead of Jordan-Wigner transform, there's many different spin to fermion transforms. I'll talk about the ones that our group has worked on. That's why it's in green. And then phase estimation has been replaced with many variational methods for readout. I'm still going to discuss phase estimation because I feel like phase estimation is one of the best places to understand what's going on if you haven't seen the algorithm, if you haven't seen quantum computing, if you don't know what quantum computers are about. I feel like phase estimation is a very close to experiment way of thinking about how a quantum computer works. Okay. So, as I said, phase estimation, I'd like to give a high-level view of what phase estimation is all about. So phase estimation, this H here is the Hadamard transform. This is effectively a Fourier transform over 2 bits. This is the inverse Fourier transform, also over 2 bits, and you read out some set of digits JK. You do unitaries that go up to different powers of 2. Goes to different powers of 2, so you can do a Fourier transform. You get out the bits that you need. So if you think of Fourier transform properties, if I want a sharper spectrum, I need to go longer in time. The same idea applies here for phase estimation. And the way that you can think of phase estimation, if you're an experimentalist, or if you haven't studied it, or if you studied it and you didn't quite understand what happened, is that it's actually computing an autocorrelation function. This autocorrelation function is being Fourier transformed, and that's what's giving you effectively a spectrum. So you get some readout, and these JKs would basically be the bits of this J of omega. There's a few caveats about how the superposition of different states goes. It's not quite the same as Fourier transforms, but the idea is still very much the same. You want to get out some information about the oscillating phase, and that will tell you about the energy, again, the frequency. This is due to Shor in his famous factoring algorithm in 1994. He uses this as a subroutine for the factoring. Katev, according to legend, couldn't get a copy of Shor's paper, and he just decides to rederive it, and he ends up with this very beautiful paper discussing phase estimation cleave at all come up with phase kickback, which is another name for the same concept. And in fact, this concept goes all the way back to John von Neumann. If you look at how he describes quantum measurement, it's very much in the same framework of phase estimation. So there's a long history of this idea being played over and over again. So to connect it a little bit more to experiment, if you think of experiments, you think of absorption spectroscopy. Absorption spectroscopy is effectively the same thing. You have, again, an autocorrelation function. Here, psi is not exactly just the wave function, it's wave function times the dipole operator, but you're still getting an autocorrelation function. You're Fourier transforming that autocorrelation function, and that will give you out peaks. These peaks will be at the energies that the system responds to, and this particular plot here is representative of this particular situation where you had some wave packet that got excited to the excited state with some momentum inside the transverse direction, and it moves back and forth inside this well as it exits. And so every time it comes back to where it began, well, the autocorrelation function peaks, and so this is the peak, and the envelope is the rate at which it leaves the well, and it has no further overlap after it goes away. So this is from Eric Heller. He was on my thesis committee, and he did fantastic work back in the 80s about semi-classical propagation and thinking about how you could actually do wave packets and things like electronic structure, vibrational structure, and absorption spectroscopy. Okay, so this is the high-level idea of phase estimation. Phase estimation has been replaced by many variational methods, which are more appropriate for near-term quantum computers. I didn't include much on it today, but it's okay, I hope. Okay. What I did include, however, is much of the work that's much closer to my heart. I also had a degree, an undergraduate in math, so I really like looking at the mathematical formulation of quantum mechanics. There's a lot of symmetry, a lot of ideas. You get these algebras, which are just taking two operators and giving you back another operator. And so here's the anti-commutation algebra, that this is AJ, AK dagger times AK dagger plus AK dagger, AJ dagger. So instead of the commutator, it would be XY minus YX. This is AJ, AK plus AK, AJ. Okay, so this is anti-commutator. And here in the qubits, we have these nice poly-spin variables, and we have this nice representation of them as qubits. And then the fermionic situation, all the nuclei are fixed, and around it is the electron cloud. And this electron cloud is basically just putting electrons into different orbitals that are describing the possible places a single particle could be. So one of the games that we've been playing for a long time is thinking about how do we do spin to fermion transforms. And we've been playing this since at least 2016, thinking about how do we discuss local spin operators for fermionic simulation, how do we understand the operator locality. We looked at different local encodings and the super fast encoding. We've implemented these on test cases. We're implementing it now to see if we can actually get some error correction as we're doing the encoding. And this has been a lot of work we've been doing since I arrived at Dartmouth. So almost every year we have a paper on this topic. And most recently, I wanted to point out our work on custom fermionic codes for quantum simulation. I think this is a really nice place if you are interested in stabilizer states. If you're thinking about spin to fermion transforms, this has a very nice connection to error correction codes, a nice connection that actually incorporates many of the ideas that we've thought about, as well as many ideas that other people have thought about. So you have these local encodings where you can have fermionic interactions that are very local, versus these non-local fermionic encodings that would occur in something like a Jordan-Wigner transform, where you end up having to apply sigma z at all the intervening qubits between along your one-dimensional fermion labeling. So this is all for second quantized fermionic Hamiltonians. And one of the things that this custom fermionic code allows us is to fill in this gap from we have no vacuum entanglement. So this is that the vacuum state is just a product state versus having a vacuum state that's extremely entangled, right? So you should think of the toric code. You ground state of the toric code is highly entangled. And if you have a toric code, and the excitations that you can have and their interactions would be extremely local or just local, period. Whereas if we have something that doesn't build up the same level of entanglement, you have these operators growing with the system size, with the length of the interaction. So that would be examples would be the Brodkin-Kettev transform, the Jordan-Wigner transform, and then there's these super fast encodings, a number of other codes for simulating fermions. So given that this is a talk that's supposed to be for everybody, I wanted to, just kind of give an overview of some of the work that we've done. Okay. All right. Next, what I want to talk a bit about is what is the competition for electronic structure versus what we're doing on a quantum computer. So I thought to include some of the experimental works on electronic structure on quantum computers, but the experimental works that people have done on electronic structure on quantum computers, well, it's been very fantastic physics and very fantastic illustrations of using a computational device. It's not very practical, right? So really think of, I actually want to go find out what the vibrational structure is of some molecule. Well, I couldn't actually do it on a quantum computer. They're just too small and too noisy. And so what I want to talk about now is quantum supremacy, but not in the sense that a lot of people have been thinking about it. So this is a quantum group here. So in quantum supremacy, quite often we are thinking about doing a task that you cannot do any other way than with the quantum computer. Here for electronic structure, this is a very practical question, right? People are really interested in the answer. They really want to know, did it work, did it not work? And so when we think of electronic structure, we should really think of the competition as being how close are we to reality? How close are we more close to reality than if we use a different method, or is this the best method we can come up with? And I would like to say that this electronic structure competition is not just about the devices, but also about the algorithms that are developed for it. And I'll give some illustrations of this. And I was asked if I could give somewhat of an introduction to density functional theory. And it also gives us a chance to talk about some of the other work that my group's been doing. Okay. So first, before I go any further, let me take a second and just state a little bit more about quantum computing and about both quantum computing and classical computing, right? So just what do we want to do? We talk about Hamiltonian set of electronic situations. So as I mentioned, we had this picture of, we had this picture of doing this spectroscopy where we have some time evolution. This time evolution is being generated by some initial state, and we evolve it in time to get some later state. We can do the autocorrelation function and get out something like a spectrum. Fine. This is something that we can do on a quantum computer efficiently. We don't expect that we can do this efficiently on a classical computer unless we have very particular states or very particular Hamiltonians. So the structure of generically is not something that we expect that we can do on a classical computer. Minimization, however, is quite interesting because minimization is quite often discussed inside of the quantum literature as well as the classical literature. And even what I'm talking about now, when I say we want the ground state, we want the excited states, we want these various states that we want to know, what is the configuration here? So what is this actual equilibrium distance here? What's the curvature around this equilibrium point? So we can know something about the vibrational states. So all these things require that we need to find the lowest energy state and the energy of that lowest energy state in order to produce this plot. This is not easy for quantum or classical computers. As Brian mentioned, there's a number of complexity classes, and this minimization problem typically falls into some of the harder complexity classes that we don't expect quantum computers can solve either. So I want to highlight this point a bit. So like Brian said, this is something I've been thinking about for many years. Since 2012, we wrote a paper reviewing the computational complexity of electronic structure. We wanted to classify how difficult it is to solve this problem for the ground state. Some interesting questions thereof. There's various algorithms for solving this problem, various approximations one can make. I'll talk about a few of them in a moment. And as you note, we have a number of papers here on Hartree-Fock method. The Hartree-Fock method is quite an interesting method because it gives a very nice concrete way of understanding electronic structure. When you go to your elementary chemistry course, you go talk to you look at some of the Nobel Prizes in quantum chemistry that involved quantum mechanics. Quite often they look at what's called the frontier orbitals, so the valence orbitals. These are orbitals on the outside of the shell. You think Rydberg atoms, if you have some Rydberg state, this is the valence shell. So this is the one that interacts, this is the one that gets all the polarizability, the one that's going to be forming some sort of interaction with this nearest neighbor. Similarly, in quantum chemistry, you should think the same thing happens. So when you do the Hartree-Fock method, you just keep track of the highest occupied orbital. This highest occupied orbital is the one that's going to be responsible for things like bonding, things like destabilizing the energy of the system if you're inside of an anti-bonding orbital. So all these ideas from Hartree-Fock give rise to our entire notion of what orbitals are. These are single particle functions. These single particle functions are normally defined through the Hartree-Fock method and generalizations thereof. The generalization thereof that's very important, that we'll get into some more detail about, is density functional theory. Nonetheless, this Hartree-Fock method is what's called NP-complete. NP-complete, as Brian mentioned, is one of the complexity classes that is expected to be difficult for both classical and quantum computers. Quantum computers are expected to have a quadratic speedup over classical computers, but that's it. Electronic structure on a fixed basis is QMA complete. This is actually the paper, if you note, the first author, Brian. We just finished this paper recently, so this is from March 15th, is when we put in the archive. And so anyways, this is something we've been thinking about for a while. And I'm going to give you some details about how this all fits together. There, okay. Yeah, so what I want to talk about now is density functional theory. This will hopefully give us some way of kind of grappling in what's going on. So density functional theory, to give some notion of what people talk about in density functional theory. Density functional theory is by far the most widely used method for electronic structure. There's a lot of ways of generalizing density functional theory. There's been many different ways of doing density functional theory. There's databases of density functional theory. There's popularity contests for density functional theory. So I wanted to give some introduction to it. And Walter Kohn is a amazing physicist, in fact. He did a lot of really nice work, and he got the Nobel Prize for his development of density functional theory. If you go to journals and you search for the most highly cited papers, the top 5 papers are about DFT, various formulations of it, various functionals, things like that. If you go to Journal of Chemical Physics and you look for the most highly downloaded paper, most highly cited paper, it's usually about DFT as well. Density functional theory ends up being the workhorse for most methods that people use in electronic structure. So when we speak of quantum supremacy, we speak of quantum supremacy in a very real sense. We really want to say, all right, all the chemists at Bayer should stop what they're doing and learn quantum computing. Well, we really have to beat density functional theory. Okay. And it's a fast method that's not necessarily reliable, or it's reliable in some sense, and I'll give some concrete examples of what sense that is. But first, let me say a little bit more about what we mean by density. So when we talk of density functional theory, we don't mean the density matrix, we don't mean a reduced density matrix, we mean the probability density. It's just the probability of one electron. And so the idea is that I'm going to take the system that had n electrons, 3 to the n coordinates, 3 to the n, plus another, another set of coordinates, another n coordinates for the spin variables, but we'll just kind of brush it on the rug for the moment. We have this density matrix, which is going to contain all the information of your wave function, allow you to do convex combinations of wave functions, probabilities over wave functions, fine. Reduced density matrix, we're tracing over particles, not subsystems. So we leave the number of orbitals the same, and we get rid of particles. So we have n minus k particles. So we get rid of all those, and we're left with just k particles. The matrix of k particles inside the same number of spaces. This is a bit different than doing the partial trace inside of qubits. So when you do a partial trace over qubits, you lose both particles and subsystems because the particle and subsystems are identified. So this is a nice caveat if you're thinking about the mathematics of what's the difference between fermions and qubits. So finally, the probability density is normally normalized to n, the number of electrons in quantum chemistry, instead of 1. That's fine, not a big deal. And normally this probability density refers to the ground state density. When we say density functional theory, it's normally talking about the ground state density. Okay. So to give a little more of an introduction to density functional theory is really this very beautiful hack to say that we don't need to care about the wave function at all. It's actually almost amazing when you think about it, that we can just get rid of the wave function for the entire discussion. But it's amazing, and it's also true, and it's also almost trivially true. It's trivially true in some sense that you can get rid of the wave function, but if you want to know anything about the system, you probably need to go back and compute it, right? And so it's a bit cheap. And I'll hopefully explain what the main idea is. So if we have a scalar potential, we're going to assume that the scalar potential is non-degenerate, or gives rise to a non-degenerate Hamiltonian. So again, we have kinetic plus interactions. So kinetic plus the interactions for an electronic system are always the same, right? You always have kinetic energy, p squared over 2m, and you always have some interaction, 1 over r, 1, 2. But then this nuclear part of the system is going to change as we rotate a bond, as we stretch a bond, as we vibrate or rotate. So the nuclear structure, the nuclear field that the electrons see will change from problem to problem. The reason that density functional theory works is that that nuclear potential will only couple into the electron density. You only need the electron density to understand one problem from the next. The rest of the problem, the kinetic energy and the electron-electron interaction, are wrapped up in some functional we just call F. This F, you can think, is just, if we had a wave function system here, we just take the expectation value of t plus w, and that would give us what F is. So the Hokenberg-Kohn theorem, which is actually relatively easy to prove, I'm not going to do it today, but if you take the ground state density, it says that this ground state density is in one-to-one correspondence with the scalar potential. The reason it's a one-to-one correspondence to scalar potential is that the scalar potential, whatever it is going to determine what the ground state wave function, because the rest of the Hamiltonian is fixed. So you just need to give me the scalar potential and I can tell you what the wave function is, assuming I could solve the whole problem, yes? And assuming the whole problem solves to something that's unique, then I can actually prove a theorem that says the ground state density, by going through this path, scalar potential, solve for the ground state wave function, integrate everything out, and get back to ground state density. Well, that means that this is also in one-to-one correspondence with the scalar potential. It's a bit cheap, but again, it's just because the density is the only thing that couples to the problem-dependent part of the Hamiltonian. Okay. Taking this a little bit further, if we consider practical density functional theory, you can't quite use that construction. You need to introduce what's called a Kohn-Sham system. The Kohn-Sham system was introduced in 1965 by Walter Kohn and Lou Sham. And what you do there is that you actually bootstrap from Hartree-Fock. So I mentioned that I like Hartree-Fock a lot. Well, Hartree-Fock is very nice because there's not as many approximations as you might find inside of density functional theory. So in Hartree-Fock, you basically have some way of computing self-consistently, and I won't get into details of self-consistent field method, but the self-consistent field method is an NP-hard, is an approximation to an NP-hard problem. So here, the idea is that I have some system that has kinetic energy, potential, and some interaction. I want to map it to another system that has kinetic energy and a new scalar potential, but no interactions. The idea is that this one gives rise to a wave function, so the exact system gives rise to an exact wave function. The exact wave function gives rise to a density. If we construct a Kohn-Sham system correctly, then the Kohn-Sham wave function, a slated determinant, which is probably too small to read, so a slated determinant is also in one-to-one correspondence with the same density as the interacting system. So the Kohn-Sham systems only reproduce the density, has the same, the state is the same type as a Hartree-Fock state, and applies in static and time-dependent cases. This is a very brief introduction to density functional theory, but hopefully it gives some notion of what's going on here. Ooh, does it fit? It does. Yeah. So what I'd like to do is connect a bit of what Brian talked about in the very beginning and what are the limitations of density functional theory. So I mentioned that quantum computers cannot solve ground state problems efficiently, just in the worst case scenario, just because QMA is a very hard family. But Norbert Schuh and Frank Strade write this very nice paper in 2009, Computational Complexity of Interacting Electrons and the Fundamental Limitations of Density Functional Theory. So there's a proof sketch here. I still have 5 minutes or so, so I'm going to punt here and just say that it's a nice proof. It goes through using the Hubbard model, the Heisenberg model, and some in the QMA 2 local Hamiltonian. And you basically reduce from one system to the next system to the next system. They started off with the electronic structure Hamiltonian, and they found a model that gives rise to the Hubbard model. But if the thing that I would like you to note is that in all these cases, this bi.si is the magnetic field that's acting locally on each electron spin. And that's actually a pretty strong approximation. And just to punt on the actual proof, it's not so important. The takeaway is that once you allow for these local fields, if you can get that universal functional, if Arthur has access to universal functional, then he's as powerful as Merlin. He's as powerful as Merlin. He doesn't need Merlin anymore. That now, if he has a computer that can compute the exchange correlation functional, the exact functional here, F, then he doesn't need Merlin anymore. Merlin's no longer needed. He can actually compute it on his own. And again, this is the functionals that you take a map over all wave functions that give rise to the correct density, and you compute the expectation value of the universal part of the Hamiltonian. Now, Brian mentioned, so coming back to the paper that we just finished, so this problem remains QMA hard to solve even without local fields if we're allowed to adversarially fix the basis. So if we pick a basis that's very bad for you, then it can be QMA hard for you to solve. Okay, so this is still a bit of a stretch. It's not quite the most natural problem because normally you would pick a basis that makes sense. But in this case, we can at least show that it's QMA hard. So we made some progress in that direction. And all this is to say, that the electronic structure problem for density functional theory is also not trivial. Okay. I would like to say that one thing that we have also thought about inside of my group quite a bit is instead of density functional theory, which we know is QMA hard, we thought of the computational complexity of time-dependent density functional theory. And this was also some work that I did back in 2014. And there we're thinking about the computational complexity of density functional theory. It's just a summary of Frank and Norbert's paper. And maybe a bit more pedantic than theirs, but nonetheless, the idea is that we've been thinking about the difference between density functional theory and time-dependent density functional theory quite heavily. So time-dependent density functional theory, of course, you allow your system to evolve in time, but now what you need in order to use TDDFT with a quantum computer, well, you can take your quantum computer, which can time evolve a system, given some input state that is necessarily easy to compute, and some external potential that changes in time. Well, you can compute the output state, and you can't measure the output state. The output state's very hard to measure just because of the size, but you can measure the one electron density efficiently. If you measure the one electron density in time efficiently, then you can actually compute what the force is needed to be to recreate the same dynamics on the density at all times. So you plug in your density, second derivative of the density, so that's your acceleration. And the acceleration is telling you what forces you need. You have a force balance equation. The forces tell you what the density has to be, what the potential had to be. So the gradient of the potential giving us the force. And that force is then telling us what the cone-Sham potential needs to do to make sure the density follows whatever density we're supposed to be following. Okay, also have some nice movies there. This is a project that's going on. Uh-oh, I'm getting pinged for time. Yeah, 5 minutes. Okay, great. That's good because I'm about done. Okay, yeah. This is not the slide I wanted to end on. I have yeah, I will end there, but I want to plug one quick thing if I can. We have postdoc positions. I also have a very large group of people who work with me, and I wanted to say something nice about them and just highlight them just a little bit. So a lot of the work that I just described has been done in my research group, and we've had a lot of fantastic people working there. And I can share one quick screen here. Okay. Yeah. I didn't get a chance to copy in, but I just wanted to highlight that we are taking postdoc applications. If this is interesting, if you want to think of this further, different Fermionic spin transforms, thinking about test sets, how do we actually evaluate the performance of quantum computers versus density functional theory? How do we evaluate density functional theory in the aggregate? We're doing some work on neural networks with Tim. Riley is doing the spin to fermion transforms. We have a number of undergraduates in our group. June's been doing our TDDFT explorations. Joshua is an incoming postdoc, and then Kyle and Weishi are junior graduate students, as well as a number of undergraduates here, and here, and here. Tim's done really nice work looking at neural networks. So in any case, if you're interested in a PhD or a postdoc, please shoot me an email. And then I would like to end with thank you. So acknowledgements of the funding agencies, NSF for supporting my work, Department of Energy for supporting my work, and of course, people working with me and myself have been supporting my work. So we've all been happy to present some of the work that we've been doing. So I think we're about on time. And so I'll stop here and open up the stage to questions.
Great, thanks, James. Yeah, are there any questions?
I had a quick question. So I was wondering if there's the NP problems and the P problems. I was corresponding to maybe what we can solve with maybe DFT versus a fully quantum solution. I was wondering, I guess, if there's maybe like a middle ground for like hybrid methods, like where you have kind of a sphere of where you're calculating quantum mechanically and the rest is calculated classically, if there's like some maybe middle ground in computational difficulty.
Yeah, that's a really interesting question. There's a lot of people pursuing that with things like DMFT, where you're going to do some embedded region. Also, if you even think of protein folding. So I mentioned protein folding is somewhere where it's all classical. But if you think of a protein, right, it's all classical until you need something to bind. When it starts binding, you're going to have quantum mechanics enter. Or if you have light matter interaction, you're also going to have quantum mechanics entering there. And so your active region where you'd want to treat things with quantum mechanics right now is still being treated with density functional theory. The rest would be treated with classical mechanics. But this problem that I mentioned about computing QMA hard problems, whether it's with the quantum computer or classical computer, still the same problem. Right? You still want to get what the ground state energy is, or with the excited state energy. But you still want to get the energy, whether it's with density functional theory or with quantum computers.
Thank you.
Yeah.
May I ask a question? I would think that classically TD-DFT would be like one step further in terms of the DFT. So you were, it seems that you were trying to suggest that TD-DFT would be like better on quantum, which is completely non-intuitive from a classical viewpoint, isn't that? Yeah, I just wonder what is the intuition? How could this happen?
So the intuition here is that if you actually look at density functional theory, it's a very well-worked horse. People have thought about density functional theory for many, many years. Time-dependent density functional theory has many more approximations you have to take on top of density functional theory. You make this adiabatic approximation, you assume that there's no dependence on the initial state. A lot of approximations you have to make in TD-DFT. You make these approximations because time dependence is much harder to compute than the ground state. The ground state has many special properties. You only need to compute the ground state for one system, every system once. Whereas for time-dependent dynamics, you need to compute it for every different field you put in. Right? So you need to really think about how these different fields interact. And so the notion that TD-DFT would be better on a quantum computer than DFT is because DFT and the ground state problem is QMA hard. Doing time evolution is exactly what we expect quantum computers to be able to do. That's exactly what we expect quantum computers to be able to do. That's what it means to be BQP. In many ways, you can say the quantum simulation problem itself is BQP.
I see. So in this sense, it might also be a good idea to directly simulate the whole system instead of try to find any ground state to begin with. Maybe
right.
It's a good idea to directly apply the dynamics to whatever physical system we have.
Yeah, that's exactly right. So if you think of TD-DFT, there's no initialization problem per se, right? There's an initialization problem if you need to find it, but if you just given a system, you can then do the time evolution, right?
Yes.
And so this is the idea. This is the difference between finding the ground state and then evolving after that versus just saying, whatever state you give me, I can do the time evolution. That's the right way to think about it, I think.
I see. That's very helpful. Thank you.
Yeah, glad to help.
James, I have a question. Hi, this is Brigitte. Thanks for a nice talk. So I have a question about your spin to fermion transforms, the local ones.
Yes.
So do they get rid of the overhead of the Jordan-Wigner? Can you say something about the scaling of any overhead they might have?
Yeah, so I can say something really interesting about it. So if you think of actually building a torque code, some sort of error correction scheme.
Okay.
Normally, when you think of how this is phrased, it's phrased in terms of Majorana modes to begin with. Right? So in some sense, when we get to asymptotically large quantum computers, we're talking about error-corrected, fully fault-tolerant quantum computers. There, you don't need to do a spin fermion transform anymore, right? The entire thing's built with Majoranas effectively,
Right.
so you don't need to do it at all. And so what we're thinking in this model is some way of interpolating from a fully, from a full torque code all the way back down to an unentangled state.
Okay. So are you using error correcting codes to construct these? I mean, you're saying they're stabilizer states, right? So they are discrete finite stabilizer codes?
So if you think of the torque code itself, the excitations you get are flux and vertex excitations.
Right, right.
You put them together, you get a fermionic excitation.
Oh, okay.
You can skip building them individually and just build a Hamiltonian that builds them
Oh,
together.
I see. Okay.
Then
I
you
get
have
the
to
idea.
think about what couplings are being allowed, what the actual underlying graph is, and then how you're actually going to move fermions inside that space.
Right. I see. Okay.
Yeah, it's a cool paper. I'd say check it out for sure.
Did it cause any complications in the Hamiltonian expression?
So in many ways, I guess all the spin fermion transforms don't really change the Hamiltonian per se, right? It just changes the fermionic operators
Well,
in front of it. So.
You know, it depends whether you put the operators on the Hamiltonian operators or in the states, I guess.
Yeah. Yeah, but the coefficients for each term are still the coefficients for each term, right?
Okay. Yeah, that wouldn't change.
With the
Okay,
cost.
I'll check it out.
Yeah, awesome.
Thanks.
James, maybe I'll ask you a question that maybe the organizers had asked you. But if you were to appoint somebody to work on a problem that would help you out, what would be the problem you would assign to somebody else?
This is being recorded, right? No, but in all seriousness, one of the problems
we won't bind you to your answer.
That's okay. I mean, whatever. If you guys steal it, you steal it. Okay. But the idea, one of the ideas that I think would be fantastic to do is actually just to do a test set of molecules, the same test set you perform on density functional theory on a quantum computer, right? Win, lose, or draw, right? So density functional theory is not very well characterized theoretically. Past what I explained to you, after what I explained to you, you just start making approximations for this universal functional. Make them. Make it up yourself. In fact, there's a popularity contest where you just weight the new functional by the popularity of all the old functionals. And then they just test it out, right? So there's a lot of data science that goes into just testing over, molecular instances. You get all these single point calculations like I showed in the beginning. There's a table of a few examples. If you ran all those examples on a quantum computer, you could ask, what is your mean squared error? Right? How far are you off from TFT, right? And this wouldn't necessarily be something that would be something, wouldn't be good, right? You wouldn't expect it to be good, right? You have a device that has 57 qubits. How are you going to put on 100 orbitals? You might have to compress it or whatever. But then after you've done that, you get out errors. And you can actually say how these errors are performing from year to year to year. With method to method, you could even fix the device and test out with different methods and actually see how this evolves. So this is something I would think is a great PhD project. In fact, I just gave it away yesterday. So we'll see how that goes.
Maybe I have a quick question.
Please.
Yeah, so a great talk, James. So I'm not sure I still understand very well what QMA complex means, but it seems like you said that the complexity depends strongly on the choice of basis. Can you comment a little bit on that? So
yeah, I mean, Brian's here, so we can also comment quite a bit. But the idea is that if you think of the electronic Hamiltonian for chemistry, we actually don't have very many handles on the problem instance. So the reason that DFT works is that you have the scalar potential that defines everything. And the scalar potential is only defined over 3 coordinates, right? So X, Y, and Z coordinates that defines all of this. But this is for a system that has 3n degrees of freedom in the wave function. So if you think of what was the original proof encodes other problems into this local spins. And you now have a spin degree of freedom for every single site inside the system. So to think of where we could actually construct a way of putting other instances into the problem, Well, we needed another way of handling it. And so one of the ways that we did this was actually encoding into the basis that we picked. Or should I say, Brian?
Okay. Thank you.
That's the main idea, that we needed more ways of actually inputting problems.
Yeah, and a small thing. So the previous work encoded the instance in the magnetic field, and that's what we were trying to get rid of, because that's sometimes in condensed matter systems there are magnetic fields that we consider, but generally in chemistry, there's not, at least in a first approximation.
Yeah, even the way they included it was also quite.
Yeah, it was very like site specific and very, very, very precise. It wasn't just like some global thing.
Thank you.
Of course.
Maybe another question I have, James, is if I think about, we're in the NISQ era, so if we're short of having a computer that can just solve everything, we think about devices that might be well suited for solving specific problems. So I guess you gave one idea that maybe if you're specifically working on like a toric code platform, then maybe you have in hand what are essentially fermions already. So that simplifies your treatment of fermion problems.
Yeah.
If I think about, I guess, other constructions that people are thinking about for quantum computing, are there some, or as NISQ devices, are there some that you think hold more promise specifically for a chemistry solution? I mean, one that comes to mind immediately is I work in cold atom physics, so you can imagine, well, I guess a gas of fermions has got to be a great initial choice for simulating the property of electrons in a molecule, but maybe I'm wrong.
That's exactly what I was thinking. When you think of cold atoms, these analog simulations, these are quite interesting, but I think one of the things that makes cold atoms more appropriate for condensed matter, and you're experimental, so you tell me what the progress has been, but I know that a lot of times to control the system, you're doing control to make systems that are very close to condensed matter systems, where you really have only 2 or 3 parameters to set the Hamiltonian. Whereas electronic structure, we really need to have very fine tuning to understand what the spring constant is. So we need to perturb the nuclei just a little bit. And so we need very small handles on all these different parameters of the system. I think as the analog simulators get better in terms of the control, it may be very possible to actually have that level of fine control to actually perturb the system slightly in a way that you control, in a way that you want to actually see what happens as you stretch a bond, or as you rotate a system, or as you vibrate. These are all the sort of motions that you might want to know for a molecular Hamiltonian. And I think the main idea is that you need to figure out how to engineer the potentials that would then allow for this coupling to occur in these very small values. Like the Hubbard model, you just have T and you have U. So 2 parameters versus having M to the 4th parameters.
So a question on that note actually is like, so like I know ultra cold chemistry is starting to be a thing, and in that you can start to really look at how the fine structure and the hyperfine structure of the individual atoms affects the chemistry, and maybe also look closer at transition states. Could that be, I guess, a potential like database of information to then inform these kind of computations?
What I think would be really cool is, so as I mentioned, density functional theory is just benchmarked on instances, right? It's benchmark on things, right? So you could really ask questions of density functional theory, how well it does on these benchmarks that you couldn't have had experimentally characterized before, right? You really start to see how hard you can push computational physics classically and how well you might be able to match it on a quantum computer. So I think that's fantastically interesting. Think about how do you actually put hyperfine states into molecular systems.
So, there's the big question, I think, is, what types of chemistry problems will we be able to do with quantum computers that we can't with classical computers? And so, you described some, what our classical methods are or what our quantum methods are. Where do you see, like, how do you think we should, structure the search for, this holy grail in my mind that would, get us to practical quantum advantage in the context of chemistry.
Yeah, so as I pointed out, right, I think that this idea of getting practical advantage, right, practically means doing the practical problems that you can do classically now, right? So the practical problems you do classically now, not every functional is good, right? If you make a random functional with just random parameters, it may be very terrible, right? And that's also a basis to compare against, right? You have all these instances that you should run, you run over and you see what your mean squared errors are. This is not to say that these problems are tailored for quantum computing. I think that's the wrong way to think about quantum supremacy, personally. I mean, I wouldn't use a computer just to solve one thing. I'd use a computer to solve everything. I mean, you turn on your laptop, not because you just use it. You don't have one laptop for Zoom and one laptop for Word and one laptop for, watching Netflix. You have one laptop that does all the things, right? So I think if quantum computers are really quantum supremacy, it should be able to at least do the classical computation as well as a classical computer can. I think for your question more directly, I think if we're thinking of things that quantum computers should be better for faster, I would say doing time dynamics would be something that's much more in line with what you wouldn't be able to do classically easily, right? So you expect worse errors on time-dependent phenomena in general, right? So you just have TD-DFT just not being as well developed as DFT, and you can imagine quantum computers beating TD-DFT much sooner than beating DFT.
Yeah, no, I think it's a balance, right? I mean, of course, for practical advantage, you don't want to choose problems just because the quantum computer can do them better, but of all of the problems that we try to do classically, maybe some of them are more suitable for quantum computing than others, or efficient practical quantum computing than others.
Yeah.
Either based on the structure of the problem or the devices.
Yeah, and that's exactly why I think a test set would be interesting. So if you have enough test sets, you can say, well, this test set, it didn't perform as well. This test set, it did much better. This test set did the same. This test set, it doesn't work. This test set. So really making testing of algorithms, testing of devices the same way you would classically, I think is really the right time to do it now. Right? So that's an advertisement for all of you graduate students and undergraduates who need something to do in quantum. Start running benchmarks on every device you can find. And then just say which algorithms work better than you would expect classically, which algorithms worked as well as you could classically, which ones didn't work at all.
So how do you see exactly, benchmarking for problems that we can't do classically, right? I mean, we run on a quantum computer, we run it on different computers, different algorithms, we get some numbers. But if the hardest problems that, we have no comparison to, is it like experimental data that we'd be judging things by? Or?
So that's how people judge classical computers, right? I mean, people are doing Hartree-Fox since before there were actual computers. People were doing it by hand. Hartree's, I think his father was an engineer and did the integrals for him by hand. One of the papers he thanks the computer, but it's the Royal Academy of Astronomy. I forget what the English name is, but these are the astronomers who are computing tables for longitude and latitude problems, and they did the computations for it, right? So the point is that it's not about how good your computer is, it's about what you can test out now, right? And I think the early Hartree-Fock algorithms and the early Hartree-Fock methods, they didn't compute anything that was amazing or anything that was really interesting, but the same way that quantum computing is now. I think there's a very nice roadmap of how to develop quantum computers following how quantum computers, how classical computation developed and the algorithms for classical computation. I think there's two questions. There are also algorithms, right? Umesh?
Yeah. Sorry, I had to come back to something you said about dynamics. So is there a canonical question in quantum chemistry that you would think of with respect to dynamics, where, which would be the most important one to solve, or one where quantum computers could help the most?
We're on the line with a lot of experimentalists. So a lot of spectroscopists here. So I don't want to say anything too off, but spectroscopy as a general question requires time dependence, right? So depending on what field it's interacting with, depending on what system it's interacting with, well, you're going to get some time evolution after that, right? So you hit it with the neutron and you see what happens, right? So this would be a time-dependent example, right? So a lot of examples of spectroscopy, and thinking about what examples of spectroscopy we can actually simulate better with quantum computers, classical computers, brings us directly to this ideas of vibronic sampling, right? So this is boson sampling reformulated for molecules, right? So you can start thinking of what sort of spectroscopy you can do with the quantum computer. I think this is going to be much closer, but then you're really getting this question: what's an experiment and what's a and what's a computation.
But you can also fall into a trap where a lot of the dynamics that you might launch by a spectroscopy measurement are actually just small perturbations, you know, with a lot of the electrons basically being spectators and following along and doing the same thing. And maybe it's one electron dynamics or something. And then I don't know that it really, I mean, you're the chemists, whether it explores that much more deeply the difficult parts of representing the molecule. So I don't know if it's maybe more like, yeah, I don't know, dissociation is that kind of a much more disruptive event or something.
So I was going to answer not with my chemist hat on, but with my theory hat on. So thinking about ground states, right? If you think of ground states, you get a lot of really nice special properties, right? You get area laws, you get these certain things, you get a lot of approximations you can make if you're just talking about the ground state. When you start talking about a random excited state, you get hard random states that can be as hard as you want them to be, right? So you get a lot of large.
Yeah, sure. No, my concern is, do you get a random excited state, or do you get a one electron only so slightly excited state? You know,
how much energy?
It's one thing to explore the very bottom spectrum. It's another one to say, you know, I have a molecule and I place every single electron in some excited orbital and I shake the whole thing up. That's way out there in the excited state spectrum, and yeah, that would be hard to describe.
Yeah, but that might also be interesting. So I think one of the things that I can say, I think kind of addressing some of the questions that Brian brought up, and also what you're saying here, is that what people have explored in quantum chemistry are what people can explore in quantum chemistry, right? So when quantum computers really go beyond classical computers, you can start asking new questions, right? You can ask, what happens if I actually hit it with the hammer of a laser and now the electrons are all inside of different excited states that you couldn't have asked any other way before? Maybe just you explode the system, you don't know why. I know thinking about smoking, you have all these radical molecules that are formed, and this is still an open question about how this process occurs. And this is just because you have so many things happening at once. It's very hard to keep track of all of them. But when you really have a way of doing dynamics really well, maybe you can get the reaction rates, the entire reaction network, and the entire dissociation network of what happened in a way that you wouldn't have even dreamed of classically. Right? If you went back to the 1920s and asked Douglas Hartree, what do you think people can do with the computer? There's no way you would have thought you could simulate, you know, as many orbitals, as many atoms as you can now, right? So the point is that what he dreamed of back then, we're way beyond. Because just like even a computer, right? There was, I think, around the time that he was doing algorithms, people were like, oh, we don't need any computers. IBM didn't patent the personal computer, right? This is, you know, I think there's a whole lot of vision that comes from having better sight.
Mm-hmm. So at 1:40, we've gotten to the point where we often ask the more graybeards among us to leave and allow the students and postdocs to interact with the speaker more. So maybe we got to that point. But let me just intervene by offering my extreme thanks to James and Brian. I think both the intro talk and the seminar talk were like exactly of the kind that just allowed a lot of people to ask a lot of questions and engage in the discussion. So thanks for a great seminar.
Yeah, thank you again for inviting me.
Yeah, thanks, James. See you
Next time in person.
Yeah.
Thanks, James.